Hello, everyone. We're here today to talk about what happened this year at ICLR 2022. There were some great papers, great presentations, and a lot of noteworthy ideas. I'm Nick Vasiloglou, VP of Research ML at RelationalAI, and I'll be with you for the next 20 to 30 minutes in this presentation. So if we had to describe ICLR 2022 in keywords, this is what we would find. The neural ordinal differential equations are getting a lot of traction. Diffusion networks, these are fairly new ideas that are becoming more and more successful. We see papers that have to do with security of deep learning models, like as backdoor attacks. But I have to say that if there were like the king and the queen of the conference remain language models and self-supervision. Big surprise? I don't know if it's really a surprise, but maybe we should have expected, is slow growth of papers around molecular, protein, drug design, all of them kind of fueled by research for COVID. So if we had to describe ICLR in a nutshell, we would say that right now, we feel that we can do self-supervision on every type of data and every type of network. This is very important because self-supervision studied 4 or 5 years ago with language models, and now it's the de facto training of neural networks, and we're going to see a lot of new things that interesting things that came up, and we can do it for every type of data. So self-supervision is here to stay, and the results are stunning. If I had to categorize, so, you know, just like for the process of creating this presentation, and there's going to be a blog post follow-up, is, you know, we read the papers, we shortlisted them, we tried to define them, to put them in different categories. You know, I'll just like enumerating: self-supervision, language models, sparsity, question answering with reader retriever, vision transformers, molecule protein drug design, reinforcement learning, diffusion models, distribution shifts, some fundamental, you know, there's always new interesting fundamental concepts and advances in of ML, and just like other. Of course, my presentation is a little bit biased. I don't talk much about the vision papers. I don't talk much about reinforcement learning, which took a big chunk. But if I had to do something like that, it would be probably 4 to 5 hour presentation. So I just also want to make a disclosure. You know, right now we're just kind of like hitting the limit. Making this presentation was worth 100 hours of work, just going through titles, abstracts, and then understanding the, you know, the concepts behind the papers. What I've noticed that a lot of papers try to make clear statements with their title in an effort to surface the message, because there's a lot of information clutter. And, you know, a lot of papers do a good job by either providing a very clear bullet list of their contribution, or some visuals, you know, 1 or 2, you know, graphics that make the concept or the key idea of the paper very clear. There were some papers that they looked interesting, but required a lot of time to go through them. These papers, unfortunately, they get lost into, you know, the sea of information. I feel like we are hitting the wall where soon we're going to see papers that their job is to go through a conference and do what I did automatically. So basically, every conference will be a new data set for summarization. We're not there yet, but hopefully we will get there. So let's start with self-supervision. You see the word mix-up over there, which is a very popular technique in self-supervision. It was discovered probably 1 or 2 years ago and it's here to stay. Again, for those of you who don't remember what self-supervision is, typically what happens is that you have a few labeled images, not that many, as you see here. But then what happens is that from these labeled images, unlabeled, actually, from a lot of unlabeled images, you can create, like you can take and create a jigsaw puzzle, you can scramble it, and you can create a network that the job is to unscramble it. Okay, so you can create infinite number of data, because here's your input, and you create the label mechanically. And there's all sorts of things. This is one way of self-supervising. As we're going to see, there's many more. Okay. Now with mix-up is an old idea. So basically, if you had this data point and this data point, the idea was, well, create a new data point, which is a linear combination of these 2 points. Okay. And if there was a label for that, the value of the label would be a linear combination of the 2 labels. It turns out that most of the times adding noise in machine learning can have some really good results. And basically what the authors are doing over here, say, well, if you have these 2 points, create another point close to this one. So add some noise here, add some noise there, take this, the linear combination value, and then do noisy examples. And, you're getting better results. Anyway, have we seen noise working in our favor? Yes. The noise in stochastic gradient descent that we use all the time is called stochastic because there's noise, also proved to be very beneficial. Differential privacy had some really nice guarantees. So noise is good. Now, the other problem we're having is, we talked about, the self-supervision technique where I'm taking the image, I'm scrambling it, and I'm trying to predict the permutation. I can, sometimes people convert the image into black and white and they're trying to predict the color. Sometimes we call that augmentations. Or sometimes we're just taking, the rotation of the image and we're trying to make sure that the label doesn't change. Now, not all augmentations are beneficial. Okay, sometimes the self-supervision or the wrong augmentation can have catastrophic results. So this paper talks about a technique where I believe they're using reinforcement learning, trying to find what are the right augmentations for your data set. So, a little bit of extra work, but very useful. Something else that was really, really striking is what I call the reverse dropout. We're all, if you think about it, dropout is another source of augmentation or self-supervision, because basically you're taking a network and occasionally you are setting some weights to 0. So you're dropping some connections and you're training it that way and your network learns better. But when you have tiny networks, and believe me, you're using tiny networks everywhere on your cell phone or your smart watch. We can't really use dropout, because if we use dropout, then what happens is we hurt the performance a lot. So we do something clever. So we're taking this small network and we make it a component of a bigger network. Okay, so we train this big network and then we cut out that piece and we put it into production or with fine tuning. So I call this reverse dropout, because during training you have more weights than the inference, which is the reverse thing that happens in dropout. Now, some of you might be familiar with a very kind of like a seminal paper, the SimCLR, where this idea, SimCLR brought a revolution in self-supervision, especially for ImageNet. So what people would do is you would take the input, you would run 2 augmentations or no augmentations or another augmentation. You would pass it through, the same network, and you would ask for the network to make these images the same. Okay, and if you were changing too much, you would demand from the network to make them very different. And apparently, training the network like that and then fine-tuning it with a few labels give you much better performance rather than if you were training for labels from the beginning. So we knew how to do this with images. We didn't know how to do that with tabular data. Okay, so I consider this as kind of like not the first, but one of very important self-supervision techniques for tabular data. And just a hint about how it works. So basically, you're taking one element of your tuple, and you randomly replace it with, you sample it from the distribution of that column in the data set. So if, for example, you had a Gaussian bell curve of ages ranging from, I don't know, 5 to 20 years old. Actually, it wouldn't be Gaussian, but approximately Gaussian, whatever distribution. You would just go randomly and, flip it and get a value from your distribution. And you will demand that the output of the network wouldn't change that much. Simple but clever, but works pretty well. Now, I'm not going to get into the details. Again, whenever you see the term SSL, I mean self-supervised learning, there is a bunch of self-supervision techniques already known about graph neural networks. Okay. And this paper talks about how to pick the best one. So again, trying to find the right self-supervision techniques. GANs used to be quite remarkable. Like back in 2014, they dominated a lot. The field. They created a lot of excitement. Then language models came, and we kind of forgot about them. Like they went out of the spotlight. This is not a 2022 paper, but there was a 2022 paper that was based on this one. So whenever you see this term guest paper, it means that in order to understand the current paper, we have to go back and find out the original one. And this is really great because, this paper combines like GANs and language models. They're both generative models, okay? So you have a MLM, means mask language model. So you basically have a language model that predicts a value for the mask. But then you go to the discriminator, okay, and the discriminator, sees these words, and it has to find out whether this was like the original or this was the one that it was replaced by the mask. Okay, so the discriminator doesn't know that the mask was here. Okay, obviously, and that's how you train it. And apparently, this is a great way of training a language model. So you're using the whole GAN technique, but you're basically trying to fool the discriminator. Like, if your language model becomes that good, then your discriminator shouldn't be able to predict whether it's original or replaced. So it will have like a 50% accuracy. So that's like your goal. Your goal is to train your generator so that your discriminator achieves like 50% accuracy. It's useless, cannot really tell the difference. Very clever idea. Now, another really interesting paper, which is very practical. And I like this paper because for those of you who work in practice, in real problems, you come across this situation where, imagine that you want to build a classifier for cats, lions, and dogs. But quite often, you don't really have that label. You have a label that, it's a domestic animal, or it's a wild animal, or it's a Bengal cat, I don't know. So you don't really know the information of the label, but you know another information that it's linked to your label through an ontology. And in some cases, it could be that it's a wolf, the wolf is a canine, and the canine is a dog. Okay, so how do you infuse this this ontology into your classifier so that you can still use these weak labels, because not exactly what you're trying to do, but it's linked close to what you do. Okay, so it's useful to identify that something is a wild animal. It helps you, feel like that's a lion. Again, interesting paper, and we don't have time to go through that, but somehow there's a way to embed that ontology into your classifier. Now, I really love that when the researchers are always skeptical and they're pushing things to the border. So, everybody talks about self-supervision. Self-supervision is great, broader evolution, but do not overdo it. And what the researchers here from CVU are talking about is, look, if you know your already, like if you have an idea of your end task, of the downstream task, as they call it, it's fine. Do pre-training, but don't wait too long. Okay, don't overdo it. Start introducing your final objective earlier. Okay, so make use of that. Another interesting and practical example. Now, this could have been on a different section of the presentation, but I put it over here. For those of you who have been doing data science for the past, 10, 15 years, you remember one of the problems was you have unbalanced data sets, or imbalanced, people call them. You don't have enough labels. And they were all sort of strict, you were using labels like as equal sampling, there were rules and stuff like that. Well, guess what? It turns out, and you can see some amazing results over here, that if you do self-supervised learning, this is kind of like the gap. I think that's what we're seeing here between training and test, and you can see that by doing self-supervision, you can actually, in some cases, the out of domain behaves better than training. So yes, so this is an unexpected collateral benefit of self-supervision, that it helps a lot with learning with imbalanced labels. Now, we didn't go through all these papers. Again, there's going to be a more detailed presentation. This is kind of like the short one, but here's a list, the paper, the PDF of the presentation which is going to be available, of 21 papers that we selected. You probably saw 4 or 5 here, maybe more. But it's, if you have more interest, the papers exist in this presentation. You don't see them now with my notes. Now, obviously, self-supervision became successful through language models. So the next thing over here is language models. So we see more transformers. And if we had to describe it in a nutshell, we're going to say that transformers become more and more scalable, more predictable in case of stability, more expandable, and editable. So you can just go and add and delete facts. All that things happen if you put into the game what people call vector databases. Okay, so it seems to me that we found a recipe that make language models more productionalizable, if you want. It's like philosophically, in order to put something in production, it has to link to a database. Like everything goes into production through, not everything, but most of the systems go to production through a database, if you think about it. So that seems to be going to that direction. So this is a paper that basically tells you that if you find mistakes inside the language model, you want to fix them, and by fixing them means that if there's a fact that it's wrong or it's false, you want to delete it. You don't want to spend $10,000 to run it in CPU. It has to be fast, so you don't want to compute all the gradients. And obviously, if you fix that, you don't want to break something else. And the paper makes an effort. I can't say they provide 100% guarantee, but they're getting there. I think that's something that they need to work. And they basically provide a technique where you can shrink the gradient. The other problem is, we're all familiar with the GPT paper where we're training a huge language model, and that solves all the problems, that has a lot of, can solve many tasks. But that turns out not to be the truth. Okay, so there's kind of like a limit, and it's a little bit ad hoc. Okay, so sometimes the downstream, you tune for something, or you self-supervise the maths. You can solve one downstream task, but another one gets hurt. So it's not in this presentation, but we do have the new Gato from DeepMind. We're going to make a different session for that supposedly solves that problem, but not yet, at least not until ICLR 2022. Now, we could have put again that paper in self-supervision because that's what it is. Usually when you train a language model, you're trying, you're given some words and you're trying to predict, I don't know, the next 4 or 5 words. But what they're doing is like a really, really simple trick. This is what is amazing about this field. So what they're doing, yes, you have your first, I don't know, 10, 20, 512 words, and you're predicting the next 5 or 6 when you train or you mask it. But what you can do is we can take these 5 or 6 that you're trying to predict and just do kind of like a cosine similarity, like text similarity, like with a bag of words. And you can find another like phrase somewhere else in the document. So instead of like predicting these next 5 words, you predict another 5 words that you find somewhere else in the passage, okay? And you see there's like a big lift in the F1 score. So simple, I think it was a 5x here they mentioned. Another really interesting paper. So we thought about, language models working on a linear sense, predicting words and answering questions. But this paper shows how you can teach other kind of concepts. And I think the easiest one to understand, they talk about colors. Like you can, so you're saying this is the word and the answer is right because the one is on the right side. It's actually on the bottom right. Okay, and then you give the same thing. You give this word, you give this word, and then it kind of like starts learning the word right. So here you give it this one that hasn't seen before, and it does answer left. Okay, because you're pointing to the left. It can also learn north and south, and yes, you can see it over here. It got like it can learn the concepts like left, right, leftmost, and rightmost. And the same thing for colors. Okay, here's the northeast and south. So another kind of like interesting, and again, this is GPT, so it doesn't really have a 2-dimensional transforming here, it's 1-dimensional. I bumped into this paper while reviewing another paper, which is not here, but that's also a very useful application of, so let's say this paper of transformers is, somebody's giving you text and you can create an ontology out of a text space. Very interesting and very practical. Now, here is a very kind of like delicate idea is, okay, it's fine, you train a language model you're using, but if you go into production, things are changing. Obama used to be the president, then was Trump, now it's Biden. You have to make sure that things are kind of like changing and you are correcting them, okay, without retraining. And so I think the authors here, basically they started working on a benchmark in order to motivate and advance the research in this area. And they basically, this is T5 and GPT-2 that they're working. They're basically having a way to add and remove. So you want new facts to get in and other facts to change. So we can always see that as an incremental maintenance of language models. And it's very important because nobody wants to pre-train from scratch. Like, you know, keeping a knowledge base active and correct is not an easy problem. Even if you're in the discrete domain, you know, it's even harder to change that. Okay, so again, it's kind of like natural to think about, okay, we have the language models and we have the graph neural networks. Is there any way we can put them together and reason over a knowledge graph? Yeah, well, it turns out, yes. So you do have your language model here, and you change it a little bit. So, you know, your graph knowledge becomes a GNN that gets into the input. And again, gets into the end. This is the same over here. So not rocket science over here. You're combining the two architectures. There's some little details, but it doesn't really matter that much. Now, what's interesting is that we are going to see another paper later on, or we have it in the presentation, maybe we wouldn't go through that, actually claims the opposite. Okay, that, you know, the GNN doesn't help in the reasoning. You can use a simpler network. It's an interesting finding. Yes, there is another one. This is a little bit more complicated, but it's called the Q-former. Basically, we, you know, when we have a transformer, we have the attention layer, and we have multiple heads, 10, 20, it doesn't matter. But you don't always need all of them. And actually, it hurts the performance that you do have heads that they're not useful. Each head is supposed to be looking at something that it's conceptually meaningful. And the Q-formers, they basically use another attention to learn the number of heads that you need. Another interesting paper, you know, you might have seen, there was even a recent paper that depending on how you ask a question on a transformer, you can get different results. In fact, there was this paper where you ask a question and you have a very, you know, low precision or accuracy. And then if you add the phrase, let's think about it step by step, it goes, explodes, and it starts kind of like a reasoning better, starts to reason better. And here the authors introduce an intermediate layer that, you know, kind of like rewrites your query or what you're asking, trying to make it consistent so that you're always getting a stable response. Again, interesting direction. This paper is the paper that every Kagler has been waiting for. I'm talking about Kaglers because Kaglers really like, you know, boosting or bootstrapping or bugging. And, you know, obviously here they trained, you know, different birds, and not all, you know, they obviously, because of stochasticity and other, like on the same data set, same parameters, they don't get the same bird, they're different. So basically they're bootstrapping. So they train, I don't know, 20 different birds. And that gives you some nice confidence intervals of your predictions. Very straightforward, interesting, and works against the worst robustness. And this is kind of like a paper that basically demonstrates that if you really want to do code generation, you know, a language model is not enough, but you do need basically other components that kind of like compilers to check about constraints and they validate the code. I don't want to get into the details, but it's a nice architecture that basically, again, makes language models more stable and more reliable for another task. That's what we need to keep over here. And again, we're getting toward the end of the transformers section. Is the fact that you know, transformers learn everything, and they have it somewhere in their weights, but it's always nice if you can explain what they know and what they don't know. So what this paper is doing is it's basically having an attention layer that attends over a huge vector database. But obviously, if you attend to all of them, you can attend it on inference side, but not on training, because training will create like a huge attention layer. You can't differentiate it, but that's fine. While they're training, they're finding some nearest neighbors, and they attend over them. So basically, they give up differentiation, or part of the differentiation. Obviously, the rest of the network is differentiable, so that they can tap to a database. And again, the results are stunning, amazing. You can go correct them, you can trace them, you can. This is like very important during production time. You can hot replace facts, add facts. A lot of things come as a perk. And for those of you who have seen my presentation from last year, we talked again. There was a workshop. So this idea is based on the 2020 paper about memorization, where the idea is you train a language model, but at inference time you consult a big vector database, and you can see that you're getting much better results by basically training a smaller model, but using a lot of memory. Has a lot of nice facts. Now, and this is the follow-up paper of memorization. And basically, the idea is not only you are consulting a vector database, but now you're consulting or you're taking information from Ontology, like a graph database. So in order to improve your results, because the vector database sometimes may contain errors, by filtering and using an ontology, you can make it even more robust. Again, getting towards production. And another idea is that you might have some pre-trained concepts, and when you are making a prediction, you're only attending into your fundamental concepts. This is called the concept transformer. So you might lose something in accuracy, but you can always interpret. And this is a paper that, again, it's borderline language models and self-supervision. For those who know me, I have a real sweet spot for theorem proving. I believe that this is kind of like the epitome of AI. It's one of the hardest problems. And my thesis is that a lot of systems will be based on the principles of theorem proving in the future. And the idea is here that the cost of acquiring labels is really enormous. If you really want to get labeled data, it's about 2.5 man-years per megabyte. This is how much it costs. And I want kind of like kind of worry with a lot of details, but there is some self-supervision techniques. These 9 different self-supervision techniques that they're using, and they get like 50% lift in the success rate. And I believe this is the last one, the last paper for this section. Am I wrong? Yes, this is the last one. All these years, we become all fans of beautiful soup. You get a document and we strip off all the HTML information, and then we do what we do. But we forget that HTML is there to HTML hides knowledge, which we are proudly throwing away, and there's no reason for that. And now we know that it's probably much better when you do pre-training to maintain your HTML, labels, because these are things that help the model learn better. Again, here's a list of 31 papers. You will find information about all of them in the presentation. with my comments. Probably the most, I don't want to say successful, but interesting, or attracts a lot of interest, if you want, application of language models like question answering. And there's something called the reader retriever model, which we presented in a previous presentation. And obviously it's based on a transformer. In a nutshell, this is about 2 or 3 years old paper. The reader retriever and retriever are fundamental blocks of question answering. We see more and more papers that they use a hybrid of knowledge bases and text in order to answer questions, which is really great. It turns out we need both. You know, knowledge bases have the advantage that they're like very well structured, clean, fast access. We can store them. We can, you know, people know what's there. You know, we have decades of experience with databases. But sometimes knowledge is complicated. I mean, we don't speak SimCLR, we speak English or whatever language you speak. It's much more richer and complicated. And there's, of course, things that we need to express that we can't really express in a formal language. So we need to have, we also need to have text. Not everything can go to a knowledge graph. Okay. Now, and in this lecture, we're going to see, you know, the paper that I think was the most important. If I was the reviewer, I would give it the best paper award. I really like that, the concept. But again, it's a personal opinion. Obviously, you know, you've seen my excitement with all the papers so far. It's, you know, this paper that combines basically any buzzword that starts from R in machine learning, but has really good examples, results. So something that combines relational, rules, recurrent, reinforcement, and reasoning components to give the best results. So we're going to see that too. Now, you know, in order to understand the reader and the retriever, we're not going to the details, is, you know, you have to go a little back to the fundamentals. Like, you know, if I have a query and a document, I have two options. Either embed the query and embed a document, and then try to find or train it based on the nearest neighbor distance, okay? Which is nice because nearest neighbor distance, we can build fast access structures, you know, vector databases. It's very interpretable and all that stuff. Or if I need to know if a query and a document are the right results, I can put them in the same network, and I can, you know, I can find whether they're right or not. So basically, I can take my query and all possible documents, and I can rank the documents based on that query. I mean, as you can understand, the nearest neighbor has the advantage that it's like a simple nearest neighbor sets to find and rank, I don't know, the top 20 documents. The other one requires, you know, a very, very heavy network comparing all the documents together. Okay, obviously this one has more accuracy because it's a more complicated network. And don't get me started with the Euclidean distance and the space and the complexity of the space. The nearest neighbor Euclidean space can take you that far, you know, not far away. So, but of course here you have faster, you know, speed. Here you have accuracy. So what people do is, you know, what we know what to do. So you get the retriever. Maybe you retrieve the top 100. And then you have a better, you know, similarity function to rank them properly. So that's like the reader, retriever, and ranker. So you have a ranker over here. Okay, and they kind of like do it in an adversarial way. That's the way you train it. It doesn't matter that much. So that's exactly what this paper. There's another paper working on the same idea, and but here they play a game. In the first one, I'm trying to match the documents and the queries based on the bioencoder. So the bioencoder is this, and then I'm creating some labels that I'm training my cross encoder. Again, the cross encoder is this, and then after I train this, I generate labels and I train the other. So like one is training the other and it's playing a game. And now we are in that paper that I was talking about before, where they basically claim that in question answering, combining a language model and a GNN is not really, the best idea. They're using a simpler, we call it the counter network that has better results. Okay. This is another paper that is, you can think about it as multimodal question answering. So I can either do visual search, which is find me something similar, but here I give instructions where I say, well, I want this, but I want this to be in cream color. Okay. So again, there's a network. It's fairly easy to straightforward to understand how we can do the same thing. Okay. Again, I will keep mentioning that the concepts in AI are becoming more stable and more practical. Everybody talks about knowledge graphs, and the first thing they talk about is like triple store. Okay, so I have subject, predicate, or relation, or fact, whatever, object. Okay, but in reality, if you ever work with real relational enterprise data, you will see that the relation can have 2 or 3 keys. Like, it can be a tuple. Basically, it needs to be stored on more than 3 columns. And unfortunately, most of the GNNs don't accommodate for that. So that's like a paper that takes that into advantage. So they call it hyper-relational because if you have more than 3, it means that more than 2 entities, they all related to each other on the same tuple. Okay. Very interesting paper. We like papers like that when they cast this problem differently. So for entity recognition, they use what I call the inverse reader retrieval model. So, reader retrieval, I give you a question and you're trying to find the passage that answers that. Here, I give you a passage and you're trying to find questions, like kind of Jeopardy, and based on the question, you can find the entity, okay? Because the question is it that entity? Is it that the other? Interesting, because it kind of like, if you train a question answering system, then you can also use it for another task. Isn't that what the transformer brought in our life? You train one model that can answer a lot of things. And now we're coming to that paper, the R5. I feel like this paper will be discussed in the future. I might be wrong. But it's called Rule Discovery with Reinforced and Recurrent Relational Reasoning. And that's why they call it R5, because it has 5 words that start from R. And the idea is that, you're given like facts. And it constructs a graph and it tries to navigate the graph. Obviously, uses reinforcement learning, not too heavy one. And as you are traversing the graph, whoops, you realize that these are the kind of like rules that I can infer. Okay, very important. Like rule inference has a lot of applications, and you see down here the results are, they're beating almost every other solution, by far. I mean, look at this. The rules and recall is close to 100%. This is kind of like an epiphany moment compared to all other systems. Okay. Again, here is a list with the papers. And next stop is the vision transformer. So basically, it's not the first time we see them, but it looks like they're here to stay. Okay, this is kind of like a provocative title, the end of convolutional networks. So basically, one of the problems with vision transformers was that it was taking an enormous number of resources to train them. Okay, much heavier than ResNet, let's say, and a lot of data. So it was very expensive, and in the end, they weren't getting as good. They were a little bit worse than the state of the conference. But there were two findings in the fundamentals of deep learning that they basically made them better than convolutional networks and faster and less resource hungry. And there's something called the sharpness aware minimizer and the mixer MLPs, multi-layer perceptrons or fully connected layers. And basically here they show you the ResNet. This is the vision transformer. It doesn't have really a nice smooth, loss surface. And basically, if you add these two concepts, we see that the it becomes much smoother and much easier to train. And that idea, this was a 2021 idea. The idea is that you're using a fully connected layer. And actually, they did that for vision. So you take your image, you split it into patches, you pass it through. You see over here, you scramble it. Okay, so you create these channels over here, and you create different MLPs by taking patches from all of them, and you keep mixing. So that's what is happening. Like you keep, you're taking the output of your MLP and you keep like shuffling it and creating new layers. This is actually, we don't have it here, but that idea was also presented in a paper called D-Light, which basically showed that you can use a transformer with only one head by using this mixing trick, okay? And the other thing is a special regularization where basically what it does is it takes the loss function, the surface you see has all these spikes, and it says, well, if you're taking a descent direction, I don't want to see sudden changes, okay? I want you to take me to directions where the error doesn't change that much. And that smooths out the curve and apparently makes everything much, here the results from last year, and it shows, lower. These are significant kind of like improvements on the loss functions in different benchmarks. And again, once we challenged the ResNet, the next thing was to challenge the GANs. And basically, this is kind of idea of you're using a vision transformer to train a GAN. Some simple findings over here. Again, there's more papers than that. This is a choice of 5 papers that I put over there. And we're getting closer to the end. Molecule, protein, and drug design, redesigning physics and biology with AI. And again, as I mentioned at the beginning, COVID has sparked research in the area of AI and biology. This is about creating antiviral drugs. I don't know how familiar is the audience with the domain, so I don't want to get into details. Unfortunately, in order to get into that, we have to talk more about the essentials of drugs and how they work. The next one we see it is for antibodies. Okay, similar concepts. Graph neural networks, basically, I think was in the previous and this one, graph neural networks. Now, this is an interesting paper where we know that AlphaFold was a big project. AlphaFold 2 solved a lot of problems. Now they focus on a smaller problem, kind of like after AlphaFold, where everybody can run without having to spend, thousands or hundreds of thousands of dollars on GPUs. Again, it's for protein docking, and they talk about some benchmarks on COVID. Now, again, here's kind of like using GNNs for atomic simulations, and here the atoms and the molecules that they're trying are basically, protein molecules, like long ones. Another kind of like interesting, that's not related to COVID, but I like this idea where basically somebody is looking at your DNA and is trying to predict whether you're going to have some kind of like brain. I think they focus on brain disease, which is a very interesting problem because right now we don't really know by looking at your genes whether what the phenotype is going to be, what is going to be expressed and not expressed over there. We all know that if you want to progress science or any domain, you need benchmarks. So here they created a benchmark for drug design, so people can try different algorithms. And finally, if you really want to systematize the domain, you have to use a knowledge graph at some point, like an ontology. So everything we know about about proteins and biology can be expressed in a knowledge graph, and that knowledge graph, can augment any task that you are trying to solve. Very interesting paper. And here's again a list of papers that you can go through. And we're going to finish with two areas, like the fundamentals. This is very fundamental. If you ever work on a classification problem, you usually train, I don't know, accuracy, but in reality, you get about like F1 or AUC or precision recall. Most of them are not differentiable, so you can't really optimize them. But what people are doing is they're trained GNNs that they approximate these functions, and then they're using these surrogate functions in order to optimize for F1 AUC. Brilliant idea. It's really surprising we haven't done this all these years, but very clever trick. In fact, I argue that if you have any other business objective, you can learn that business objective and train your model to directly satisfy that. So there's something in here. Scenario I really like, in an MLP, you're basically having a network that it's like the same architecture, but with different ways you're repeating the network. In a recurrent neural network, it's again the same. If you unfold it, it's an MLP, with the only difference is that all the layers have the same weights, share the same weights. That's the only difference between MLPs. And apparently here they're running some tests and they're saying, well, maybe we got that wrong. We don't really need all these parameters. Like if you repeat the parameters of the fully connected layers, which is like the recurrent neural network, you get pretty much the same results. I consider this as like a provocative paper, which definitely deserves more research. And again, the list of papers at last. This is kind of like a fascinating domain where you're having this cover image, and I'm taking this secret message, which has zeros and ones, and I can somehow create this perturbation. And I add it to my image. So these two images visually, they're the same. But then on the other side, I can decode it, and I can, obviously there's some noise over here, but I can still read the initial image with this echo. Maybe I can figure it out. And basically here they show you two images, and this 36.2 is the P, I think it's kind of like the bit rate or the number of bits that they have, they find the limit. So here they can store 4 bits per pixel inside this image. They look identical, but you can hide information that has this entropy. This was like a great paper. This graphless neural network teaching all the MLPs new tricks. So it's quite fascinating how MLPs appear everywhere. Like if you get them right, like I talked to you before that maybe you don't need RNNs, you can just use MLPs as before. We saw the mix-up MLP that ends up actually behaving better than convolutional neural networks. Here, they're kind of like replacing a part of GNNs that it's really computationally and memory-wise annoying, and inference makes things ever slow. And they replace it with an MLP and performs really well. And they kind of like seems to be a pattern. I found another paper. It's called Bear to DNN, where for a specific task, where basically you're trying to predict, you're having input, mask, output, so you're trying to predict the mask. So the input is pretty stable and limited. You can take the whole BERT, distill it to an MLP that takes the two inputs and makes an output. And basically you can run the whole BERT with just like 4 layers. Again, mind-boggling, how you can do that. The last one has to do with an area that I actively do research, and it's something that we have worked a lot at RelationalAI to excel. Is I call it notation. If you are working with deep neural networks. If you're working with deep neural networks, and you might have used already the ainsum notation, which makes this has been in PyTorch for many years now. We saw the paper makes the tensor manipulations really really easy. And it's a great leap forward that people are working on that. And maybe in another presentation, I will talk to you more about how we can do that with relational algebra. Actually, if you look at last NeurIPS, the DBAI workshop, CEO Mohammed has a nice talk. We'll work together about how you can do that. So again, a list of papers. I want to thank you for attending. And there's going to be much more details where I cover more papers in the future. Again, you will find the slides and everything online. Thank you.